Let's try to solve this problem so that we will have a better understanding on the plane frame analysis. In this example, we would like to determine the displacement at point B. This frame is made from material that having modulus yang 200 GPa and having cross-sectional area equal to 60,000 mm², area moment of inertia equal to 400 times 10 power 6 mm power 4. In this frame, point A and point C are being fixed to the wall while point B is free to move. And this frame has been loaded with 100 kN per meter at member BC. The first step that we have to do is to draw the free body diagram, to label the nodes and elements, as well as to determine the degree of freedom. Let's have a look at point A. Point A is being fixed to the wall, meaning that it can't move in X direction, it can't move in Y direction, and at the same time, it cannot rotate. Therefore, UA equal to 0, VA equal to 0, and theta A is equal to 0. Similarly, at point C, as is being fixed to the wall, thus all the element is equal to 0. UC equal to 0, VC equal to 0, and theta C equal to 0. While at point B, it's free to move in all directions. So UB is unknown, VB is unknown, and theta B also unknown. So in this case, we are having 3 degrees of freedom, which is UB, VB, and theta B. The second step is to obtain the stiffness metric for each element. So for element 1 is between node A and node B. So we have to refer to our global K-frames matrix. So as we connect the element from A to B, so the first column is for UA, second column is for VA, and third column is for theta A. Fourth column is UB, VB, and theta B. It's always X, Y, and Z directions. So for first element, we know that UA, VA, and theta A is equal to 0. Therefore, to simplify our calculations, we can eliminate this column and the row. As our interest just want to determine the displacement at point B. So we can eliminate the column for UA as well as the row for UA, as we're not going to calculate or to determine the reaction force. So we also can do the same thing for column and row VA, and also for column and row theta A. So that for element 1, we just need to solve these 6 parameters. While for element 2 is between node B and C, and as we decide to connect it from B to C, so our column also started from UB, VB, theta B, UC, VC, and theta C. And then similarly to element 1, we just need to apply the boundary condition at the beginning so that we can simplify our calculation. So in this case, we know that UC, VC, and theta C is equal to 0. So that we can eliminate those row and column, so that for element 2, we just need to solve these 9 parameters. In order to solve for those parameters that we have identified that important in order to determine the K1 and K2, it's better to put all those values into the table so that we will not miss any parameter. So from this table, we can solve all the needed parameters, including the B and the K value. Remember, B is equal to EI over L cube and K is equal to AE over L. And of course, we also have to determine the theta. Okay, as we want for element 1 is from A to C, so the theta is 45 degree. For element 2 is from B to C, so the theta is equal to 0. So C is equal to cos theta, S equal to sin theta. Then we just need to multiply according to this value C and S. Then we have to refer back for those the identified parameters from the K global previously. So we just need to replace with the value that we have put in the tables and replace with into this equation so that we can solve for our K1. And then we have to do the same thing for the K2. Just need to refer back to our K matrix, those the identified parameters that we need to solve, and then just replace with this with the value that we have identified in the tables so that we can obtain our K2. Next step, just need to combine these two matrices in order to obtain the reduced global stiffness matrix. So in this case, we call it the reduced global stiffness matrix because we have reduced since the beginning, meaning that the K1 here is already the reduced K1, K2 also the reduced K2. Thus, the K global here automatically is the reduced global stiffness matrix. Before we can set up our system linear equation, we have to solve or to obtain the equivalent forces and moments at the relevant nodes. As in this example, the frame has been loaded with a distributed loads 100 kN per meter at member B and C. So by using the equation that had been discussed previously, where the first term here is for x directions, meaning that the force in x direction. The second term here is the force in y direction, and the third term is the term for moment at point B or at the first node. The fourth term here again is for the second node or node C in this case. The first term is for force in x direction, and then force for y direction, and force the last one is for the moment. The force in x is equal to 0 is clearly shown in the figure. We do not have any force in x direction. That's why the formula is always 0 for the x term. So by using this equation, we know the P is equal to 100, L is equal to 12 meter. So we can use this value and obtain the equivalent forces and moment. So as these distributed loads occur between B and C, so we can say that the first term here is for FBX, followed by FBY and MB for the first node B, and followed by FCX, FCY, and MC for the node C. It's always X, Y, and Z. So it also can be represented by using this diagram. So we have FBY, MB, FCY, and MC. They have no loads in x directions. Next, we can set up our system linear equation F equal to KU and solve the problem. So we want to solve for UB. So check for UB. So UB here related to force in x direction. So we do not have any force in x direction. So that's why FBX is equal to 0. While for VB is related to FBY. So we check, in this case FBY is equal to negative 600 kilonewton. So we put negative 600. And theta B is related to moment at point B. So we just need to refer moment at point B is equal to 1200 kilonewton. Then by using the calculator, we can solve the unknown displacement or the deformation at node B or the point B as shown in this slide.